Hello student, welcome to my summary of supersonic flow over airfoil. As we discussed in class, we have when we have area increase in flow, we have expansion waves or Prandtl-Meyer expansion fans. So this expansion fan increase the velocity, decrease the pressure and temperature and density. So the Prandtl-Meyer function is given by this equation nu, and the relation is that theta, which is the change of angle of the flow, is equal nu mach 2 here minus nu mach 1 here. And nu mach, this function is given in a online calculator or in, let's say, uh, uh, isentropic table at the end of the book. In class, I described how to obtain pressure and temperature uh, and density for Prandtl-Meyer function. But here for, let's say, for the Mach number, we can use this relation and Prandtl-Meyer equation to obtain the Mach number. The maximum nu the maximum nu corresponding to the Mach going to the infinity is given by this relation, and the maximum theta correspond to the maximum nu minus nu at Mach 1 corresponding to the minimum nu. The minimum nu correspond to Mach equal, let's say, 1, where the nu is equal to 0. And we have airfoils. Over the top surface of the airfoil, when the area increases, we have expansion waves. Here you see the expansion wave because on the top of the airfoil the area increases. On the bottom of the airfoil the area in front of the flow decreases, so we have a shock. On the top, the area in front of the flow increases. On the bottom, the area in front of the flow decreases. So on the top, we have expansion. On the bottom, we have shock. And at the exit, uh, we have shock on the top because again the flow area decreases, and on the bottom we had expansion. But these two are not very important because the first two, expansion and shock, determines the pressure over the top and bottom side of the airfoil. And and please note that we want expansion on the top because pressure drops. We want lower pressure on the top of the airfoil and higher pressure on the bottom of the airfoil. For this airfoil, lift per unit uh, width is equal P3, P on the lower, minus P2, P on the upper, C, the length of the cord, multiplied by cosine alpha, and drag is Pc minus P3 minus P2 C sine theta sine alpha. Alpha is the angle of attack. This is not zero because we had waves. Due to this wave we have drag force. For let's say flat plate airfoil. For diamond airfoil, this is a diamond airfoil. This diamond airfoil, on the first part we have shock on the top and shock on the bottom because the flow is symmetrical and the geometry is also symmetrical. And here we have expansion because the area increases. The area increases from here to here is 2 epsilon because 1 epsilon goes up, 1 epsilon goes down. The turn angle is 2 epsilon. The bottom also turns by 2 epsilon, and we have two shock at the end which are not important because they influence after the airfoil. We are interested on the airfoil itself. Drag of a diamond airfoil has zero lift because it is symmetrical, and let's say pressure on each part Each corresponding part on the lower and upper are the same. Drag of this airfoil is equal to P2, P2 is here, L sine epsilon minus P3L sine epsilon, it is P3, or it is equal P2 minus P3 T, where T is the thickness of the airfoil, and CD is obtained from this relation. CL is 0 because alpha is 0 and the flow is symmetrical. In class I try to show you some cases with non-zero uh, lift. Okay, and we had another theory called linear theory, which is obtained from compressible flow potential method. In this theory, the Cp is given by 2 theta over sqrt of Mach square minus 1, Mach infinity square minus 1. Theta of the upper is dz upper, dx minus alpha angle of attack. And theta of the lower is minus dz lower dx plus alpha. It is Cp and it is Cl. Cl is 4 alpha over sqrt of Mach 2, Mach infinity to minus 1, and alpha is in radiant. In Cl, thickness of airfoil, everything doesn't contribute. Only angle of attack contribute. In CD is equal for alpha 2 over sqrt of Mach infinity power to minus 1 plus 2 over the same function of Mach integral of 0 to 1 dz upper dx power 2 plus dz lower dx power 2 dx over c. So drag coefficient is a function of uh, dz dx on the upper and dz dx on the lower of the airfoil, and power 2 and second power of alpha. dz dx upper is tangent sigma u is equal sigma u. We call it sigma u. So CD is drag over Q infinity over C is equal 4 over function of Mach as shown here, alpha 2 plus 1 over 2 sigma upper 2 plus sigma lower 2, close the bracket. And this term is called sigma upper 2, this term is equal sigma lower 2, these integral terms. Okay, and total drag is dragged due to lift, dragged due to shape, this is dragged due to shape, and dragged due to viscous, and yeah, it is the induced drag due to the lift is this term. This term is drag due to the lift. Drag due to the shape is these two terms. Drag viscous, we don't consider viscous because it is let's say it is we consider inviscid flow and induced drag for 3D flows, but for 2D supersonic flow we have a drag due to the lift even for 2D flows. Okay, an alternative formula using camber and thickness is said that Z camber is equal Z upper, Z the height of the upper surface, plus Z lower over 2, Z thickness is Z upper minus Z lower over 2, and CD is equal 4 over function of Mach alpha 2 plus sigma upper sigma C bar plus power 2 sigma thickness power 2 sigma camber sigma c sigma camber is given by this equation, function of dz camber over dx. Sigma uh, thickness is given by this equation, and zt is given here. So this tries to say that drag is a function of alpha due to the lift, due to the camber, and due to the thickness. And pitching moment coefficient Cm uh, uh, point around point x0 is given by this equation, where x0 is the point of interest and uh, mc x0 m bar c x0 should be added to this. M bar c x0 is given by this relation, so it is the pitching moment. A leading edge moment Cm around the leading edge is given by this equation, M bar C leading edge. So here we should put leading edge position, which is 0 usually. And XCP, center of pressure, over C is given by this relation. Aerodynamic center is given by this relation. For let's say for incompressible flow, X aerodynamic center is C over 4, but for a flat plate, XAC is C over 2, and CM aerodynamic center is 4 M bar C leading edge over this function of Mach. And for flat plate, CL is 4 alpha over this function, so without alpha we don't have any lift. Drag coefficient is 4 alpha 2 over this function. Without angle of attack, we don't have any drag. The drag is due to angle of attack. Sigma to camber plus sigma to thickness are 0 because the flat plate doesn't have any camber and any thickness. Cm leading edge is minus 2 alpha over SQRT of Mach 2 minus 1, and XCP over C is 1 over 2. For triangular airfoil, if we have no angle of attack, we have just this drag. It is the drag of a triangular airfoil. 4 over function of Mach 2 T over C power 2. CL is 0 for alpha 0. But if we have alpha, CL is 4 alpha over function of Mach. Thank you for your attention.